All right, beautiful evening to everyone. So right here we are continuing with our classes on permutation and combination. Yesterday we started with introduction to permutation, introduction to combination, and today we want to delve deeper into this subject matter, and we'll be talking about several subtopics under permutation and combination. So I would really love you to pay real attention because today's class is going to so many exposition, and I would really love your attention. All right, let's get right into it. So yesterday, I'm sure everyone was able to grasp the concept around permutation and combination. Now I want to take you deeper into permutation. There is an aspect of permutation that involves what we call indistinguishable objects. All right. I told you yesterday that under permutation and combination, we look at the subject matter as object. So sometimes we may be talking about people, sometimes we may be talking about places, objects, things, whatever, but we always generalize them using the word object. So what do we talk about when we're dealing with indistinguishable objects? Let me give you some examples. For instance, look at this word. You can see what is right there. Success. All right. Now, if we are to permutate, of course, don't forget what I said was the other word for permutation. Can anybody in the comment section give me another name for permutation that I explained yesterday? When you say permutation, what's something else you can use to thank you? Arranging. Good. So let's take, for instance, we want to permutate these words. We have 1, 2, 3, 4, 5, 6, 7. We have 7 different objects here. But are they really different? Let's look at something going on here. If you look at these objects we're seeing right here, these two C's, they are the same thing. So obviously, this is a very clear example of what we say indistinguishable. That means they are not distinct. We cannot say, for instance, let's say I wanted to permutate this. All right. Now, let me write something else. Let me write, for instance, this is a permutation. CCSUESS. I'm sure you understand that this will be a permutation, right? I'm sure you understand this will be a permutation. Now, look at something going on here. Can we say this is another permutation? Look at something, please. This is the first C. This is the second C. Imagine I go on and I write, okay, this was the first C, this was the second C. I want to make this second C the first C now. And I'll say this C now is what I'm writing first. This second C is what I'm writing second. And I go on and write SUESS. Of course, imagine this was not C. Imagine this was, imagine this second C was I. And I used I here. Look at it. CI, IC. Now, imagine these two were not the same thing. This would have been a different permutation. But now, I have a C here. Second, let's say this was first C, second C. Now, this is second C I'm trying to write here. This is first C. These two things are the same permutation. Can you see that? They are the same permutation, and that's the reason why this is a very important subject matter under permutation. Because when you have objects we call indistinguishable, that means we cannot put a difference between which of these C am I writing first. Is this C? Yeah, or is it? So that's why we talk about the subject matter of indistinguishable object. Now look at the same thing for S. Do I say this is first S now, this is second S, this is third S? Do I say now that this S now was second S, and this one was first S, and this one was third S? You see why we have to find a way to address this carefully. All right. So how do we address this under permutation? Now, if you counted this normally, this was supposed to be 1, 2, 3, 4, 5, 6, 7. 7 different objects. If these 7 different objects are the same thing, are different, imagine it was the letter A, B, C, D, E, F, G. These are 7 different objects, all different. If I asked you, how were you going to arrange, how many different ways can you arrange these 7 different objects? Of course, based on what we explained yesterday, that means how many different arrangements can we have? That means we have 7 objects, and we are arranging the 7 of them. We're not told to arrange just 6 or arrange 5 or arrange 6 on 2. We're told to arrange the whole 7. That means we have 7 objects, we are arranging 7, which is the same thing as 7 factorial. This would have been the answer, right? Now, but in a case where we have indistinguishable object, we cannot have this now written as 7 factorial. That would be wrong. We have to remember that there are objects that are indistinguishable. So how do we handle that? This is how you handle that under permutation. You go on to have it as, you count the whole object, all right? That will be 7 factorial. Then you have to divide through with the number of objects that were indistinguishable. Look at now, we have C happening how many times? 2 times, right? That will be over 2 factorial. And then we have S happening how many times? 1, 2, 3. 3 factorial. This is how you handle situations like that. You know what this thing does? What we did, this division we are doing, is that it helps to take care of the overcounting that can happen when you want to. If you did not divide by these things, that means you will be, if you just went on to do 7 factorial, what will happen is that you will be having situations like this, where you said this was the first C, this was second C, this was second C, this was first C. And these two are the same permutation. They are not different from each other. So to take care of this overcounting, because if you counted this as one permutation, you counted this as another permutation, that would be wrong, because this is the same permutation. That was why you had to take care of it by dividing through with each of the elements that brings out situations like that, which we can see CC happened. We have just 2 of it. And then how many times can CC happen? Of course, that's 2 factorial time, where we can decide to interchange C, where we can bring, so that's 2 factorial time. How many ways can you arrange SSS? That's 3. That's 3 factorial. So we take that out by doing this division. So this is for the C, this is for the S. This is the way you solve questions under indistinguishable object. Please, is it very clear to every one of us? Because I want to throw lots of questions now. I want to know if you really understand what I just said. Can I get feedback? All right. Now, let's deal with, okay, people said not clear. No problem. It's going to get very, very clear. There's no way it will not get clear at all. It's so simple. So don't worry, just relax your mind. All right. Now, thank you. I'm going to recap. It's just the beginning. So you understand obviously that you don't have to bother at all. Now look at something. I'm going to give you another example. Let's look at the word pepper. Right? Pepper. Now, when you see examples of situations like this, where we have elements or objects that are the same being repeated, that's what we call indistinguishable. That means we cannot distinguish now which of these E are we writing. If I go on to write, let me even say I wrote, look at something, guys. Look at something, pay attention here. Let me assume this was E1 and this was E2. Of course, in my own mind, I'm the one assuming that. Now, if I say I'm writing this E2 here now as the first one, and I write PE, I said this is E2, and I go on to write PP. I said this is E1 I'm writing here now. Guys, have I made any difference? Have I written anything different? Is it different? Is this a different arrangement? If I send this to you and say this is an arrangement, this is an arrangement, what are you going to say? You are going to say no, that's not true. Like, this is the same arrangement. Now what are you doing? I'm saying the same thing. So that's the reason why we talk about indistinguishable objects, where even though in my own mind I was saying it was this E I was writing here and this first E was what I was writing here, but it still produced the same arrangement. That's the reason why we consider it under indistinguishable. That means we cannot distinguish between some of the objects. Look at the same thing for P now. When I wrote P, 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 this is 3 different P's. Now, if I went on to say, oh, you see this P, guys, this P I wrote here, wasn't this first one, no, it was this third one I was writing as the first one. And this P here, this one here, it was this one, no, it's not this one. And you guys say, okay, that was true. And I gave you the answer. I said, okay, this is another arrangement. What will you say? You say, sir, this is the same thing. All right? That's the reason why when you are dealing with this under permutation, you cannot just go on to say, normally if I gave you A, B, C, D, E, F, G, and I said, permutate this alphabet, these 7 different objects, I said, just permutate all of them. Of course, remember what I said, when I use the word permutate, I mean arrange. Give me different ways I can arrange A, B, C, D, E, F, G. Of course, you will say, okay, I have that 7 objects. You can't teach, you say this is 7. Okay, you want me to arrange the whole 7? That means I'm not arranging just 6, right? Now, you say I'm arranging everything. That will be 7 objects, I'm arranging everything. You said it was 7 factorial. You went on, you said that was good. Now, if you tried the same thing here, when you counted 1, 2, 3, 4, 5, 6, you say, okay, this is 6 objects. You now said, okay, I have 6 objects. I want to arrange the whole 6. You said this is 6 factorial. Now, you know what you'll be doing then? In this 6 factorial, these different ways, don't forget, 6 factorial will represent, for, I don't know, what is 6 factorial? 6 factorial will be like 30 times 12 times 2. 30 times 12 times 2, that's 30 times 24 will be what? Now, what about the answer that is? Those are the different arrangements that could come out from this word. Now, as good as that is, one thing you don't recognize is that in that, let's say, can anybody give me the final answer for 6 factorial? So that we can be a bit exact. What's the final answer for 6 factorial? 720, thank you. Okay, so 720. Now, 720 now, that means we can have 720 different ways of arranging PE, PPER. But let me tell you, among these 720 ways, this one I wrote here is part of it. I want you to know that this one I wrote here, where I said this object, this P now wasn't this one, because if this was an object, and this was an object, and this was an object, an example where I may be bringing this second P here as the first can happen. By the way, I can also even have another different permutation where I will say it was the third P that was this one. So can you see all those possibilities are all embedded in this 720? Every of those possibilities are embedded in this 720. That's what makes it, because this 720 considered every of the objects as distinctive object. But what we now do to prevent that over-counting, like this one, where we are counting the same thing. Actually, by the way, let me just tell you, you can still have another pepper again, written as PEPPER. We can still have another one, because if I said This was the first P where I used as the first. I said, okay, I'm doing the same, but this is the second P here. I'm doing the same, but this is the third P here. Can you see that you'll be counting this arrangement for just this changing P as the first object? I can count 3 different this thing, which is still the same arrangement. All these are all embedded inside this 720. That's overcounting, because this is 1, 2, 3. It's overcounting because this is all just one arrangement. So the way to do that in mathematics is that what we have to do is to go on now. We take the whole object as 6, of course 6, we say 6 factorial over, we now want to trim out, to remove out all these different overcounts that could happen. So what we do is that we say, okay, look at now this P now. How many P's do we have? We have 3 P's. That means we can arrange P's in 3 ways. We can, of course, you can see now that just for these settings, we can have 1, 2, 3. So 3 different ways, we have 3 different P's. So the ways to arrange those 3 different P's is 3 factorial ways. And don't forget, it's not only P that was the indistinguishable object. We also had E as being indistinguishable also. So we have to also consider that and write it as 2 factorial. Can you see that now? That is how you solve indistinguishable object. You will first of all pick everything. You count all the total object. 1, 2, 3, 4, 5, 6. 6 factorial. Then you go out to trim out all the ones that happens in this indistinguishable situation. That's what we do here. That's how you get your answer. Does it make better sense now, guys? Those people that didn't understand before, do you understand much properly now? Good. Okay, it looks like I believe everyone should be able to understand at this point. Okay, now let's go on now with solving questions. So, of course, now I believe that everyone now can give the answer to these first ones. If I ask you now, how many different ways can the word success be arranged? Of course, what you have to do is to say 1, 2, 3, 4, 5, 6, 7. We have 7 objects. That's 7 factorial over, what are the indistinguishable objects there? We have C 2 times, that's 2 factorial. We have S 3 times, that's 3 factorial. Now, if you work this, what are you going to get? What's your answer? 7 factorial. Of course, if I want to solve this, look at what I'm going to do, by the way. 7 times 6 times 5 times 4 times 3 factorial. I'm going to stop it there. The reason is because I can see 3 factorial here that I want to cut out. So 2 factorial times 3 factorial. So this 3 factorial will be cancelled by this 3 factorial. And I know that this 2 factorial is the same thing as 2 times 1. So 2 times 1, this 2 factorial we cancel. 2 times 1 we cancel on 4. We'll be left with 2. That will be obviously 7 times 6 times 5 times 2. That will be 7 times 60. That will be what? I think 540. Am I correct? Or 420, sorry. Is it 420? Or is it something else again? All right. So now that's the answer. All right. Good. For the one for Pepe that I did earlier, you understand this. So you can go on to do this as 6 times 5 times 4 times 3 factorial. You can see how to be a good mathematician when solving permutation. You don't have to be writing everything. Know how to get your work neat. So 3 factorial will cancel 3 factorial. This we cancel this, we'll be left with 2. This will be 6 times 10. That will be what? 60. All right. That's how you solve this. So let me give you guys some work to do very quickly, and that will perfect your knowledge on indistinguishable objects. All right. How many different ways? Take this question down, please. How many different ways? Please ensure you are taking beautiful notes. How many different ways can you arrange the letters in the word? How many different ways can you arrange the letters in the word? Now I'm going to write some different words. The first one will be Alabama. All right, start to solve that. The next one will be Mississippi. Start to solve that also. Then let's do also Abaja. And let's do excellence. So I would love your feedbacks as soon as possible. Okay, so what's the first one? Alabama, what did you get? What did you get as Alabama? Please write it in your maths note for that person asking. All right, this is an information we have passed across to you. All right, Alabama, you called it what? Is it 840? I can see people writing 840. Is that correct? Are you sure it's 840? Now, look at Alabama. We have how many different objects here? Well, how many objects do we have in all? We have not different because some are not different. 1, 2, 3, 4, 5, 6, 7. We have 7 objects there. So that obviously will be 7 factorial over. Now, do we have any indistinguishable object? Yes, we do. We have A. Okay, and only A was the only one. But how many times do we have A? 1, 2, 3, 4. That is 7 factorial over 4 factorial. Okay, obviously I will just say 7 times 6 times 5 times 4 factorial. Stop it there, over 4 factorial. This 4 factorial cancels this. We are left with 7 times 6 times 5. That will be 7 times 30. That will give me 210. So that's 210 ways. All right. How many of you got that? Okay. Looks like I see the answer there. Now we have Mississippi. Mississippi. So how do we do for Mississippi? For Mississippi, what you have to do again is to count each of the objects that are all present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's 11 objects, but not all of them are different. So we have 11 factorial. We cannot just leave it that way because we have some indistinguishable object there. So what do? We go on to identify all the indistinguishable objects. We start with I. We have 1, 2, 3, 4. We have 4 I's. So we have to, of course, trim that out, preventing the overcounting by dividing with 4 factorial. We see for S also, we have 1, 2, 3, 4. We have 4 S's. So we have to go on to trim that out also. We have over 4 factorial also. And then is that all the indistinguishable object we have? No, we also have P happening 2 times. That will be 2 factorial. So this is 11 factorial over 2 factorial. How do you solve this? Of course, I would advise you to have it as 11 factorial over, or let's just say 11. Just use your calculator because I think this will obviously entail so much. Of course, you can go on to beat it down if you want to. Maybe I should do it for those of you that want to see it. Let me just write, this as 11 times 10 times 9 times 8 times 7 times 5 over, okay, of course, if you know what I want to do here is I'm leaving out the 4 factorial because I'm deciding to cancel that 4 factorial with 4 factorial. So I'll be left with 4 factorial, 2 factorial. This 2 factorial, I know this is the same thing as 2 times 1. So 2 times 1 is 2. So this will be 2 cutting the 8 here. That will be 4. And of course, I know I have 4 times 3 times 2. This 4, we cancel this 4. This 2 here, we cancel the 10. I'll be left with 5. 3, we cancel 9. I'll be left with 3. So I'll be left with 11 times 5 times 3 times 7 times 5. All right. I think that can be calculated easily. What does that? Okay. Somebody wrote 3, 4, 6, 5. Okay, so that will be 3, 4, 650 ways. All right. So now what about Habaja? What do you do for that? How do you get that? I hope I'm flowing at everyone's pace. Hope nobody is having a hard time following us. Of course, for Habaja, we have 1, 2, 3, 4, 5. That will be 5 factorial over AAA. That will be 3 factorial. So I'll just do this as 5 times 4 times 3 factorial over 3 factorial. This cancels out. I'm left with what? 20 ways. Okay. And the last but not the least right there, we have excellence. How many letters do we have in the word excellence? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 factorial. But of course, we cannot leave it at 10 factorial because we have some indistinguishable objects. So we go on to identify those. E happens 1, 2, 3, 4. So we divide by 4 factorial. Do we have any other one that is indistinguishable there? X, okay. C, we have C. That'll be 2 factorial. Do we have any other one there? Okay, I can see L. 1, 2 also. That'll be 2 factorial. Is there any other one I'm missing out that is indistinguishable that I have not identified? So if you go on to do this, you should get the answer 37,800 ways. All right. So I believe at this point, you guys have been able to understand how to solve questions like this. Please and please ensure you don't make mistakes on this. All right. I told you that the basics of all these things are quite very important. It really will help you to be able to solve more technical questions that you'll be seeing very soon. Now, can you try to attempt this question I wrote underneath? How can you arrange 3 heads and 6 tails in 9 coin tosses? How can you arrange 3 heads and 6 tails in 9 coin tosses? How can you arrange 3 heads and 6 tails in 9 coin tosses? How can you arrange 3 heads and 6 tails in 9 coin tosses? Anybody with an answer there? Do you have any answer there? Quickly, while you are at it, if you have not given this video a thumbs up, please do that very quickly. That's a very great way of giving us, of appreciating the video. So give us a good thumbs up immediately, please. And let me have my answer for this question. How can you arrange 3 heads and 6 tails in 9 coin tosses? Somebody said 84 ways. Another person said 84 ways. Oh, it looks like many people are saying 84 ways. That looks like it's going to be the answer because of is the majority going to carry this? 84, 84. Everybody are saying 84. Are you sure? What if it's not 84? Are you sure it's 84? You guys seems very confident. Looks like everybody's writing 84. Nobody's writing a different answer. How did you get 84, by the way? All right. Okay. Let's see how this is going to go. We're told to arrange 3 heads and 6 tails in 9 coin tosses. So, yeah. Somebody said he doesn't understand the second question. This is the reason why I introduced this, because I want you to understand that you don't often get questions directly. And that's why you need to understand the basics of all these things. Now, you're told to toss, you are told that 9 tosses were done to a coin. Now, in those 9 tosses now, you add, look at, you took a coin. I'm sure, I don't know, probably you guys know this, but let me tell you in case you don't know. You're going to do this, any things around this in probability, which is one of the topics that you guys are preparing for. I'm sure you know that. Permutation and combination, and then you also have probability. That's under combinatorics. Now, if you have a coin has 2 possible value, head or tail. Now, they're telling you now that there was a coin. You tossed that coin 9 times. And the outcome was that you had 3 heads, H, and you had 6 tails. Tail, 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 tail. 1, 2, 3, 4, 5, 6. Now, these were the outcome of these 9 tosses. You are then told to give the number of ways you can arrange this outcome. How many ways can you arrange this outcome? 3 heads and 6 tails. Head, tail, tail, tail. This is just, imagine they told you, the person that probably said he did not understand the question. Imagine I didn't write the question like this, and I wrote H, T, 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 T. And I said, how many ways can you arrange what we have right in front of us? Like what this right here. But I say, how many ways can you arrange this? What's going to be your answer? Of course, using what we just did, indistinguishable objects, what you would have done would have been to say, how many objects do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9. You would have said what? 9 factorial over, okay, because we have indistinguishable objects. For instance, H, this is indistinguishable, T, so you would have said 9 factorial over 3 factorial, and then 1, 2, 3, 4, 5, 6, because T happened 6 times, 6 factorial. This is what you would have done if I did not coin the question out this way. Probably pun intended there, because the word coin is coming there. Anyway, if I gave you this question directly, you would have said 9 factorial over 3 factorial over 6 factorial. But what happened was, instead of giving you the question that way, we fixed it up using word problems, where we said, how can you arrange 3 heads and 6 tails in 9 coin tosses? This is the interpretation of the question. You had 3 heads, you had 6 tails. This was the outcome of you tossing a coin. More like this first outcome now, for instance, when you toss the coin the first time, based on this arrangement, this is what we're saying. Based on it, like head. So if you get the whole point, this is the way you handle it. So what was your answer? I believe if you do this, of course, it's easy to do this. You just say 9 times 8 times 7 times 6 factorial over 3 factorial, 6 factorial. The 6, we cancel the 6. We're left with 3. Okay, that will be 9 times 8 times 7 over 3 times 2. 3 we cancel 9, we'll be left to 3. 2 we cancel 8, we'll be left to 4. That will be 3 times 4 times 7. That will be 21 times 4. That will be 84 ways. All right. You can see how nice and simple all this is, right? So now this is nice and great. So this is how you solve questions under indistinguishable object. But again, mind you, let me quickly repeat again. You are not going to always get questions given directly. So be ready for twisted questions, but just understand how the whole interpretation goes. So let's go straight into another aspect of permutation. I don't believe that there's anybody in this class still struggling with indistinguishable object. I believe everybody is very fine with this topic, the subtopic we just did, right? So let's go to another different aspect on our permutation. And it is a very interesting aspect, right? This is one of the aspects you need to be very careful of, because it is very examinable. All right, very examinable. Cyclic permutation. Cyclic permutation. Please listen very attentively, because I would love to build the basics and ensure you are very much. There are things you will learn that will really give you an edge in any question you may have. Please really pay attention. This is very, very, it's something that can lead to lots of technical questions, because cyclic permutation, if not properly understood, you can mess it up. All right. So cyclic permutation, of course, if you hear the word cyclic, what comes to your mind? What comes to your mind is a cycle, cyclic permutation. Now, guys, you know the reason why this is a special topic on our permutation? Let me tell you why. If I had, let's say this was a round table, and can 7 people give me their names quickly? Just write your name down. Just write your name up. Just write your name quickly. I know. Okay, let's say there's somebody called Priest. Okay. Let me see. Give me your name. Okay, Adebola is there. Victor is here. Hilary is here. We have Johnson here. We have Purity. 1, 2, 3, 4, 5, 6. We need one more. We have Samuel. Okay, good. I think I need another name apart from Purity, because there's a P there. I don't want to start talking about that here. Peter. Okay, Dennis. I think I like Dennis, because that's a D. Now, look at these 7 different people now. Let's take, for instance, that this is a roundtable discussion. These 7 people are executives in a company, and they want to have a meeting, a roundtable meeting. Of course, look at what's going on here. There is absolutely no way for you to detect where the beginning is. Like, for instance, now, if you want to make a permutation here, do you say, when you were doing A, B, C, D, E, let me just even use A, B, C, D. Look at what we used to do. When I wanted to make arrangement, or let me even say A, B, C, D. Oh, sorry, let me just say A, B, C. You remember when I was explaining this yesterday at the beginning? I said I could have A and C, B. Do you see what was happening there? More like I used a starting point and I was interchanging the rest. That's how you were making the arrangement, where you say, okay, this was the first, this was the second, this was the third, and so on. But right here, how do you decide what is the first, what is the second? Right? How do you decide the first, the second? You can't do that, because it's a round table. You can't say Peter, I don't know who was this P anyway, or Praise or whatever, Purity. You can't say this person is the person you're going to say is the starting point. No, you can't say that. You can't say Adebola is the starting point, because they are all on a round table. There is no order here. There's no first, right? There's nothing like that. So you don't seem to know where the starting point is here. That's the reason why cyclic permutation is quite, you guys are hilarious at the comment section. I'm looking at your post and it's quite funny. Anyway, just keep understanding, that's all that matters. Right? Now we're dealing with cyclic permutation. And the big deal about it is just what I just said. You don't know the starting point. And that's the reason why it's something we have to pay attention to. So what do we do? Guys, listen. What do we do? What do we do? Because we don't know the starting point, there's something we have to do, right? You know what we have to do? We have to hold one of them. More like we have to station one of them and permutate the rest around them. Meaning that we're going to act like one of them is not being permutated. One of them is not being arranged. So the rest are being permutated around it. That means, imagine we are holding P now. That means we'll be acting like we are swapping A, V, H, J, D, and S. And we are doing all the arrangements, making V come second, making A comes next. We're doing all those things around P. That's what we're going to do. And that's why this brings me to the general equation or expression for cyclic permutation, which is n minus 1 factorial. You know why this is the case? This is the case because whatever the number of objects you are having in a cyclic permutation, you are going to delete one out of the arrangement, right? You're going to hold one. So that one is not going to be part of what you are arranging. And that's why you are subtracting one. So if you had 8 people, right? If you have 8 people on this cyclic, just around this cyclic, this round table or whatever, if you have these 8 people here, you don't want to say having the issue of which one is the first. So you just hold one. So if you had 8 people now on this round table, you will be saying 8 minus 1 is what you are permutating. So that will be 7 factorial. So obviously, if you had 7, that will be 6 factorial. So the one that you are not adding to it is the one you have held. All right? Does it make sense? So that's exactly how you deal with cyclic permutation. You hold one. Guys, please never forget this, because you will get questions like this. And when you get it, it will be disappointing if you can't answer it. This is the whole concept. The whole general concept around cyclic permutation is n minus 1 factorial. That means the reason for n minus 1 is because this minus 1 is that you are using this 1 as the old that will make you to be able to permutate the rest around it, right? So let's go on now. There's a part of cyclic permutation that I'm going to be explaining very soon, which is also very important. And let's solve a bit of questions around this, then I'll go to that aspect. It's still on that cyclic permutation. Let me give you this question quickly and let me see how you're going to do it. So guys, in how many ways can 6 members of a board of directors of a company be seated around a circular table? Give me the answer in 2 seconds. In how many ways can 6 members of a board of directors of a company be seated around a circular table? What's the answer? Is somebody writing 6? In how many ways can 6 members of a board of directors of a company be seated around a circular table? Good. I like what I'm seeing. Good. Why am I saying 60? Why am I saying 120? What is 5 factorial, by the way? 5 times 4 times 3 times 2. 5 times, what's 5 times 4? 20 times 3. That's 60 times 2. That should be 120. Why am I seeing 60 there? Yeah, I love that. I love what I'm seeing. So I believe you guys get it. So the 6 board of directors can be seated around a circular table. Do you see the word there? A circular table. So be very, very careful of reading the question properly. Be very careful. Ensure you understand that it was a cyclic permutation. They'll use the word around a circular table. All right, good. Let me give you like 2 other questions and see how you deal with it. In how many ways can Yeah, I think it's all going to be the same thing. It's always the same thing. Okay, in how many ways can 10 friends sit around a circular table? 10 friends. Yeah, exactly. 9 factorial. That's what I want to see. So on and on and on and on. I don't think we need to do too much around that. That's the whole concept. That's the whole concept. How many of you understand this? Can you give me your feedback? You really understand cyclic permutation now? No issue at all. Nobody is struggling with it. If you know you really understand it, drop your favorite emoticon or emojis, whatever you call it. If you know you really understand it, let me see it. Let me get the feedback from you quickly. Okay, nice one, nice one, nice one. Okay, all right, that's great. Now it's quite funny. See people's favorite emojis. Weird people in the chat. All right, let's get into another aspect of cyclic permutation. Now, this part is something you need to be very, very careful about. Now, we talked about a more direct one, but look at an issue that could come up around cyclic permutation. You say, what's the issue? Look at the issue. You understand, everybody here knows what we call beads, right? Is there anybody in the chat that doesn't know beads? Beads, like some of you wear it, on your wrist. Some of you wear it around your neck, necklace or whatever. Now you have beads being of this form. I told you already, I think I'm a poor artist. Probably I used to be good when I was younger, but probably. And so let's just assume this is a bead, like some of you wear around your wrist. Let's say this is a bead right now. Of course, this is an example of cyclic permutation with a different taste, right? Let me tell you what's the taste. If they tell you to permutate this bead and you try to apply the last thing I just explained without considering what this one entails, you'll be wrong. All right? Now, look at something going on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are 10 different beats, right? 10 different, arranged in a circular string. So let me ask you now, and let me see what your answer will be. In how many ways can you arrange these beads? Guys, tell me your answer. In how many ways can you arrange these beats? 10 different beats. We have 10, right? Okay. I know. Oh yeah, keep giving me your answer, right? We have 10. You can see this is 10. 10. This is 10. 10 of them there. Okay. You can see what I'm saying. That's why I needed to explain it. All right. Now, there's a reason why many of you, probably all of you, except probably a person that I saw that wrote the right answer, you are not so perfect. And let me tell you why, although I think you are still perfect depending on the context of the question. Now, pay attention to this, guys. If these beads, of course, I'm sure you know this, if these beads are arranged on a straight line, let's say this string was on a straight line and we have all the beads like this. Let's say this is 10 of them or so. I'm sure you know that the way to solve this will be what? If you have it on a straight line, this bit in a straight line. Of course, in this case, this is not a cyclic permutation. This will just be the normal way where you're having 10 different objects. And if you have 10 different objects and you're trying to arrange 10 of them, that will be 10 permutation 10. That will be 10 factorial. That's if you had it on a straight line. Now, but look at something that always happens when dealing with your bits. If you held this in your hand, let's say I fix this into my hand right now. After you are done using your cyclic permutation experience, which I saw all of you do, where you held one, let's say I held this one now, then I permutated the remaining 9 around it. That was how I got, of course, n minus 1 factorial. That was 9 factorial. Many of you gave me the answer of 9 factorial. But one thing that you need to understand is that if I held this, I was probably permutating this way, where I was making this maybe the first one, the second one, maybe this one, the second, the first one, this one, that's all permutation. You know what permutation is all about, where I'm changing the arrangement. I brought this here, and all those many things. Now, if you go on and consider the fact that clockwise and anti-clockwise arrangement, that means moving from this side, clockwise and anti-clockwise, if they are considered the same, that's a case where you have to divide by 2, because when you are dealing with beads, you don't permutate the way you are dealing with a circular table, because you can have an arrangement from this side. It's not like just moving through one direction. This direction and the other direction are considered the same. So in that case, you have n minus 1 factorial over 2. So this way, you are able to ensure that you are just dealing with just one different cant, removing the other possibility of the anti-clockwise direction, because you are dealing with beats. So all I want to say here is that when you're dealing with beats, when you see beats being mentioned in your permutation question, beats, not circular table, just know that your permutation will be not just n minus 1 factorial, it will be n minus 1 factorial over 2. That's the general concept, all right? So if you have beats, I repeat, beats, this is how you solve it. You divide by 2. Now, let me give you an example now, which will probably aid your knowledge. Look at this question now. In how many ways can 7 spherical beads? This is a question that you could always see in your exam. Somebody did not even allow me to write the whole question. In how many ways can 7 spherical beads? Once you see this written in the question, just know that even though you are dealing with cyclic permutation, you are not dealing with the normal cyclic permutation. You are dealing with the one where you would have to divide by 2, be threaded in a circular ring. Now, I want to identify something, guys. Please pay attention. Look at one thing that was written here. In how many ways can 7 spherical beads of, you see what was written here? Different colors. I want to also identify that, right? You see, let me tell you something. If you're dealing with beads having the same color, in that case, we'll be using Bonsai's lemma or polyhedral enumeration theorem, which is something we can talk about probably much later because it's not a very common situation you'll be asked. But note that I'm saying it so that you guys can understand the context of this question. You can see there's a reason why they identify that these bits are different colors, because if they have the same color, it's a different ball game. All right. Now, if somebody trying saying I should recap, well, I'm still explaining the whole concept. Now, when you have a question that says, in how many ways can 7 spherical beads? When you see this word beads being mentioned, know one thing. Of course, you can see at the end they said can be threaded in a circular ring. That means you had a circular ring and you want to thread 7 beads around it. You want to arrange it. So in how many ways can you arrange? The meaning of this thread means more like you fixing them together. How many different ways can that happen? So obviously, normally, if you were following the idea of your circular permutation, the cyclic permutation, you want to say 7 minus 1 factorial. But because it's a bead, which is a special type of cyclic permutation, you have to divide by 2. So that will obviously be 6 factorial over 2. And we have 6 times 5 times 3, times 4 times 3 times 2 over 2. That will be 30 times 12. What is 30 times 12? What do we get as 30 times 12? 360 ways. All right, good. So that is this is a special type of cyclic permutation. This is a special type of cyclic permutation. So this is very nice. Now, the most important part of permutation, the most important part, like if I'm going to, it's funny and interesting to know that if I'm going to ask you a question on permutation, this next thing I want to talk about is where you should expect tons of questions from. It's the most examinable part of permutation. Now, you would have to be very sound at cyclic permutation. You will have to be very sound at indistinguishable objects, and you will have to be very sound at the general concept of permutation. What is this aspect? It is permutation with conditions. Guys, please, if you were not paying attention, please pay attention at this point. This is the most examinable part of permutation. The most, because at this time, you would have the opportunity of making use of everything you have learned all in one question. So you would see a question I'm going to ask you now. It's going to be about Romeo and Juliet. And you guys are going to see how much interesting questions like this can get. Now, at this point, I need you to know that I expect everyone now to be very sound with permutation. So we're going to be acting more like you guys are already good with the basics. So we're going to be applying all the basics now all in one question. Now, I don't want to get with very complex questions. I want to start with simple ones. And it'll be funny when I tell you the question I term as being simple. All right. There are 2 physics books. Please, I'm really, really pleading. Make sure you're very attentive here. This part, only the strong will survive. I can assure you. And this is the kind of question you should expect in A-level. Because it brings out the best in you. Now, the question says, in how many ways can you arrange them? so that the books on the same subject are together. Now, look at this question and look at how it was framed. This is an example where you talk about permutation with condition. Now, you know what? Let me give you like 1 minute to try to solve this. I have a very strong feeling that 95% of people in this class will actually miss this. 95%. And that 5% is just is actually not even 5%. That's just me trying to be hopeful. So let me get answers. Let me give you 1 minute, try and solve this. There are 2 physics books. Okay, people have started missing it already. People have already started missing it. I'm seeing it already. Keep dropping your answers and let's enjoy ourselves. There are 2 physics books, 4 chemistry books, 2 botany books, 3 zoology books. All right. In how many ways can you arrange them so that books on the same subject are together? In how many ways? You look at it, you know why we call it permutation with condition? That means we are now given a condition that must be fulfilled. So this is not the case where you're just permitted to just do anything. Everything we have been doing, you were permitted to just do anything you want to do. You were just arranging anyhow. That means when you had A, B, C, D, if I said, how many ways can you arrange A, B, C, D? You were just doing it anyhow. But imagine I gave you a condition. I said, in how many ways can you arrange A, B, C, D such that B and C must always be together? That's permutation with condition. That means I'm telling you now that B and C must not leave each other. So in that case, you can have something like this. You must still have B and C together. You can have something like this. And you could also have this because B and C is still together here. Something of this form. That's what we call permutation with condition. So guys, again, let's solve this. It looks like somebody gave the right answer. So let's solve together. Somebody wrote 4 factorial. That's so nice. This is so nice. That's Priest, I guess. Well done to you, Priest. Now, in how many ways can you arrange them so that books on the same subject are together? Let's start, please. Please pay attention. This is something you need to really understand how it was done. It's very important. Very important. 18900, 138600. All those answers are not correct. Now let's move on. You know what we have to do? Look at let's try and identify these books because I love to always use pictures to explain things. So let's see if we can say we had physics. We have 2 physics books. So we have physics 1, we have physics 2. We have 4 chemistry. We have chemistry 1, chemistry 2, chemistry 3, chemistry 4. We have 2 botany, botany 1, botany 2, and we have 3 zoologies, zoology 1, zoology 2, zoology 3. So these are all the books we have. Now they now said, in how many different ways can you arrange them so that the books on the same subject are together? That means they are saying this should happen. Physics, they must stay together. We don't want a situation where physics comes, chemistry comes, physics comes. That would be wrong. That would not fulfill the question that was asked. You want them to, this way I wrote it now is part of, it's okay. That means you can see physics is together, chemistry is together, botany is together, zoology is together. But what we don't want is, we don't want a situation where physics and chemistry are merging together, where we are saying physics 1, then maybe chemistry 1, chemistry 2, then physics 2. This is wrong. This will not be, this is not part of the condition that was set for us. We must have all these books together. Now, let me tell you what is is acceptable. I can have physics 1 and physics 2. I can also have physics 2 as the first one, as the first book, and physics 1 and chemistry 1, chemistry 2, and so everything I have here is, let's say I write the whole thing down. That's an arrangement that is very, very okay. Now, another one that is still permitted is that I could even have it that instead of writing chemistry 1 now, I had chemistry 2, chemistry 1, chemistry 3, chemistry 4, and the same thing went on here. If you can see what I'm saying, that means you are okay. You can keep permutating the subjects among themselves. Chemistry 1 can be the first, chemistry 2 can be the first, chemistry 3 can be the first, chemistry 4 can be the first, but it's compulsory that all of them, all the chemistry books must be together. It's possible we have physics 1, physics 2. It's possible we have physics 2, physics 1, but physics must be together. It's possible we have zoology 1, zoology 2, zoology 3. It's also okay if we have zoology 2, zoology 1, and zoology 3, but they must be together. I'm also fine if I have zoology 3, zoology 1, zoology 2. If I also have, can you guys visualize what this is asking you to do? That means we want all the books to stay together. In this case, I can have botany 1, botany 2. I can also have botany 2, botany 1. So that's what we are told to do. That the books on the same subject, they must be together. That's how we must arrange them. Just like how you have it in a library. So this is like a typical library settings where you have physics put together. Then the next book, this is probably chemistry. Then the next book, this is botany. The next book, you have zoology. Now, good. Now, how do we solve this mathematically? Guys, stay tuned. Very, very simple. We have to deal with how could, like for instance, this physics now, how many ways can you do this interchanging of physics here, physics there? How many ways can you do it? Of course, because you only have 2 books, there are 2 ways. That's in how many ways can you arrange 2 physics books? 2 physics books can be arranged. Okay, let me just write this so that people can relate to it. Can be arranged in 2 factorial ways. Of course, 2 different ways. That means you can put physics 1 as the beginning and physics 2 as the second, or you can put physics 2 as the beginning and physics 1 like 2 ways. That's how you can arrange this. How many ways can you arrange the chemistry books? Guys, give me my answer quickly. How many ways can you arrange the chemistry books? How many ways can you arrange the chemistry books? 4 factorial ways. That's good. Now, that means we can have these chemistry books 4 factorial ways. That means that 4 factorial is obviously going to be what? 24. That means the meaning of that is that I could have C1, C2, C3, C4. That's a way. I can also have C2, C1, C3, C4. That's another way. I can have C2, C1, C4, C3. All those possibilities is embedded on that 4 factorial, which we have done yesterday in our introduction to factorial permutation. When we have 4 objects here, 4 chemistry books, how many ways can we arrange those 4 chemistry books? Of course, that's 4 books, 4 chemistry books, arranging the 4 of them. That will be 4 permutation 4. That's 4 factorial. That's how we got 4 factorial here. Now, look at the one for botany. We have 2 books. Of course, we are not arranging part of them, arranging the 2 botany books. How many ways can we arrange these 2 botany books? Of course, we can have it as botany 1, botany 2, or botany 2, botany 1. That's obviously 2 factorial ways. All right. Now, zoology. We have 3. Of course, look at this as object. We have 3 objects here. How many ways can you arrange these 3 objects? Right? These 3 objects. We can arrange these 3 objects in 3 factorial ways. I'm sure you guys, that's like 3 objects, arranging the 3 of them, because you are not told to arrange just 2 out of them. I'm told to arrange the whole 3. So I told you already that when you have situations like this, it's always seen as 3 factorial. Good. So that's, of course, how you first deal with this. Now, to get this total arrangement, you go on to multiply all this together. The total arrangement possible here. Go on to multiply all this first. What do you get? What do you get first? Of course, this and this and this and this. Multiply them, what do you get? Make sure you stay tuned. It's very, very vital you pay attention to what we are doing here. This is like, what do you get as this? Of course, if you do this, I believe you should get 576. Thank you. 576 ways. So that means 576 ways is the number of ways you can do all these things. Now, but there is something you must not miss out. Guys, pay attention. Are you seeing something that can happen here also? We started with physics here. We went on with chemistry. We went on with botany. We went on with zoology. Guys, are you telling me it's not also possible for me to start with chemistry and continue with physics and then have botany and then have zoology? Is that not an arrangement also? Are you also telling me that it's not possible for me to say, oh, I start with chemistry, I met next was physics, then instead of botany, I have zoology, then I have botany? That's also an arrangement. Of course, they must be together is what they said. They didn't say physics must come first, chemistry must come second, botany next, and so on. They didn't say it must follow this arrangement. They just said the books of the same order must be together. So as long as, let me write something here for people that, sorry, I want to rub this question up so that I can give you possible arrangements so that you guys can understand much better. Now look at something. We can have physics as the first. We can have chemistry as the next. We can have botany as the third. We can have zoology as the last book. This is an arrangement that is okay. All right. We could also start with chemistry and then go on to physics and then go on to have botany and then go on to have zoology, right? This is possible. I could also have it as physics, chemistry. Instead of botany, zoology, I can have zoology, botany. I could also have, do you see the number of possibilities there? I can also have chemistry, physics, then zoology, botany. Now, let me now throw this out. Guys, how many different ways can the different types of books, like what I wrote here, be arranged? How many different ways can the different types of books be arranged? How many different ways can the different types of books be arranged? All right. If you can see this, we have, if this is easy, the only reason why I'm writing all these things is because I want you to understand what's going on. We have 4 different objects. So the number of ways you can arrange these 4 different objects is obviously 4 objects arranging the 4 of them. That will be what? 4 factorial. So this 4 factorial here is dealing with all these possibilities. This is the total. That will be what? 4 factorial will be what? I think, is it 24? So we can have 24 different possibilities of arranging. If it's physics that comes first, if it's chemistry that was the next, if it's botany, we have 24 different ways those things can happen. Now, this 576 we got here was the number of ways we could arrange individuals. That means we can have physics 1, physics 2, chemistry 1, chemistry 2, chemistry 2, chemistry 1. This is 576 ways. So the way you get your final answer will obviously be 576 times 24. What does that give you, guys? 576 times 24 will give you what? 13824. How many of you got this? How many of you got this? I think I saw just one person or thereabout that got this. Okay, now you're going to do this question. This same thing, I believe you guys have this written down before I rub it off. So the same question, let me read it out for you. There are 2 physics books, of course, the same question, 4 chemistry books, 2 botany books, and 3 zoology books. In how many ways can you arrange them? That's the question. In how many ways can you arrange them? In how many ways can you arrange them? I didn't put any condition now. I just said there are 2 physics books, 4 chemistry books, 2 botany books, 3 zoology books. In how many ways can you arrange them? What's the answer? Someone said 4 factorial. Someone said 4 factorial. Yeah, this is the question. Yeah. This is what I like to see. I'm seeing some good answers there. So, can I get more answers? There are 2 physics books. Guys, I want you to really understand what was going on here. I don't want you to get confused at all. There are 2 physics books. There are 4 chemistry books. There are 2 botany books. There are 3 zoology books. In how many ways can you arrange them? Now, I want to start from correcting the person that wrote 11 factorial over 2 factorial, 4 factorial. I'm doing this because I want the person to really understand what's going on. Guys, you use this only when you're having indistinguishable objects. There's nothing like that going on here. All right? Because you don't have anything stating that. Now, I get the point that this person was actually using, and I really appreciate that effort. I think I understand the person was looking at it this way. The person was looking at it that physics was the same thing, like more like PP, physics, like the same physics books. No, but in this case, this will not be seen as indistinguishable because there are 2 physics books. They are not actually, no specification was told that probably if they are the same thing or not. So it's like having 2 physics books. Let me say, let's just assume we have 2 of you dropping your physics note now, all right, and 4 of you dropping your chemistry note, and 2 of you dropping your botany note, if any of you is doing botany, and 3 of you dropping your zoology book. Let's see it that way. I get that was what that person was trying to see that made him do this. So it's not like he doesn't understand what he's doing. It's only that he was using the concept that the physics were the same thing, but that's not what's going on here. These books are all different, just that they are of the same type. All right. Now, for those of you that you are wondering how some people got the answer they are getting, this question was very silent. They did not talk about any condition that must be fulfilled. They said there are 2 physics books, there are 4 chemistry books, there are 2 botany books, and there are 3 zoology books. How many ways can you arrange them? So you don't have any condition here to satisfy. You're not told to put them together. You're not told to make them anything. You're just told to arrange them anyhow. So anyhow, if they are together, you are okay. If they're not together, you are okay. What do you do here? 2 physics. Physics 1, physics 2, chemistry 1, chemistry 2, chemistry 3, chemistry 4, botany 1, botany 2, zoology 1, zoology 2, zoology 3. How many objects do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 different objects, and I don't have any condition. So I'm having 11 objects. I'm arranging the whole 11, which obviously is 11 factorial. You see it? So in this case now, I don't have any reason to do any other thing. I just want to arrange. The reason why I did the last question, the reason why we did it that way was because we're told that the books of the same type must be together. But in this case, we're not told that anything should happen. We're told to just arrange them. So we arrange them anyhow. Now, let me use this to get you with a clearer understanding. What did you guys get as your answer, by the way? 11 factorial is what? I see you guys writing. What was the answer you people got? I don't know why was I saying 69? Can you give me your answers, guys? What answers were you getting? What's 11 factorial? Because I don't see anybody that gave me this answer. What's 11 factorial, guys? Is it 69,300? How did you get 69,300? Guys, how did you get 69,300? Can anybody tell me? So all of you missed it. Nobody got it, except some few. Okay, some people got it. 39,916,800. Please pay real attention. I want to say something very vital here. Please pay attention. You see, inside this 39,916,800, I want you to know that the last condition we gave, of course, don't forget, it's the same question, the same books. This is the general situation where we don't care about anything happening. We're just arranging. Inside this 39,916,800, we are going to have situations where the books of the same type were together. That means all that happened in the last question is present inside this arrangement, this possible arrangement. Don't forget, in the last question, we got our answer to be 13,824, right? So we said 13,824 was the number of ways we could arrange them in such a way that the books of the same types were together. This 13,824 is inside this place. It's really inside this place because in all of this permutation we did here, this 11 factorial that we didn't do anything to. We are going to have arrangement where the books of the same types were together inside here also. So books of the same types being together is present in this arrangement. Of course, you will have look at let me tell you some situations that could happen. You can have situations where it's arranged like this, that books of the same types are together. You will also have some where maybe we have P1, P2, chemistry 1, chemistry 2, botany 1, botany 2, chemistry 1, chemistry 2. Like situations like this also will happen. So we're going to have different, that's why it's as high as this, different arrangements. It's going to be so many. So that's how you solve questions like this. Now, you are getting into the real part of permutation and combination that people used to, if you're not very solid, you could have real issues. And that's why the best way to solve and to get very great at these things is to expose yourself to lots of questions, which is what we're going to be doing in these classes. Right? Give me the answer of this question quickly. Let me see how you're going to fare with this. 6 men and 4 women are to be seated in a row. 6 men and 4 women are to be seated in a row. 6 men and 4 women are to be seated in a row. Six men and 4 women. 6 men. Just make sure you are following me. And 4 women are to be seated in a row. Six men and 2 women are to be seated in a row so that all the men and all the women are seated together. And all the women are seated together. In how many ways can this happen, guys? In how many ways can this happen, guys? Person say you never chop dinner like this. Many person attend this question, we will see if Maybe we will contribute money for her. Maybe chop dinner this night. Oh yeah, you will never chop dinner. Give me my answer. Let's say you get one person for this class we sabi permutation and combination very well. Oh. There's somebody that is consistent with great answers. Who is this person? Goodness. Who is Goodness? Who be Goodness? Do I know Goodness? Goodness, you don't write textbook on permutation and combination before. Because the guy just a throw answers correctly all this while. Okay. Okay. I don't say anything with Goodness right now for the chat. Now everybody go dey write. Okay. No wahala. All right, guys. Okay, 6 men and 4 women are to be seated. So that Goodness, don't drop your answer first anymore. Eh? Because I know that waiting everybody go just follow the that. Now, 6 men and 4 women are to be seated so that all the men and women are seated together. So, guys, tell me, how can this happen? Okay, we have, let me explain using pictures, right? We have 6 men, we have 4 women. They have to be seated on a row, but all the men and all the women must be together. So, if we have, this is the thing, we can have the 6 men, men. Please don't take this as indistinguishable object. That's one. Don't take MMM meaning indistinguishable. This is a man, this is another man, this is another man. All different. And then these are the 4 women. So this is a possibility that is very acceptable, where all the men must be together and all the women must be together also. Now, of course, how many ways can these 6 men sit? You know that it's not only one way, because this is 6 objects here. How many ways can you arrange these 6 men? That's 6 factorial ways. That's 6 arranging the 6 of them. So I just want to always, you are having 6 objects, arranging the 6. You are not told to arrange just 5 or 4. You are told to arrange, you are obviously arranging the whole 6. So that will be 6 factorial. Good. But what about the women? We have 4 of them. That will be 4 of them. We are arranging the whole 4 of them. That will be 4 factorial. Now, somebody there will say the answer is 6 factorial times 4 factorial, right? Is that the answer? Well, that cannot be the answer. You know why? Because even though this is a possibility where the men were the first and the women was the second, I want you to know that it's also possible for it to be women being the first people seated, then the men came after. So that way, you must consider that arrangement of either is it man first or woman first can happen in how many ways? How many ways can you make man first, woman? It's actually 2 ways. So that's why you multiply it with 2 factorial, or you multiply with times 2, anyhow you want to see it, because 2 factorial is obviously 2. So that's how you got 6 factorial times 4 factorial times 2 factorial. That should give you a total of what? 34,560 different ways. So I really hope people are really flowing here. Now I'm going to see who is going to get this one, because this one now is the same. It looks like this same question we just saw, but it comes with a different flavor. In how many ways can 4 men and 5 women sit in a row if no 2 women can sit next to each other? Who is not flowing? Why are you not flowing? What's up? What's going on? What don't you understand? In how many ways can 4 men and 5 women sit in a row, is praise in this class praise if no 2 women can sit next to each other? In how many ways can 4 men and 5 women sit in a row if no 2 women can sit next to each other? Okay, all right. I think she has identified herself. So what's the answer to this? In how many ways can 4 men, what about Tunji? Is Tunji right here? In how many ways can 4 men and 5 women sit in a row if no 2 women can sit next to each other? What's my answer, guys? In how many ways can 4 men and 5 women sit in a row if no 2 women can sit next to each other? Look at the condition here. We're still on that permutation with condition, guys. We are still on that permutation with condition. Look at the condition now. They said no 2 women can sit next to each other. That means it is forbidden for you to see 2 women sitting next to each other. You have 4 men, you have 5 women. How could you do this? What's going to be the answer? Everybody waits for everybody waits for the goodness. Goodness never drop answer. We never see correct answer seen. So can you imagine? Secret don't come out. Okay, I'm seeing answers. I never see correct answer. Oh. I never see correct answer. Wow. Wow. Aduaka Hilary has broken the deadlock. Okay. Okay, that's good. Anonymous, you better goodness no day for you today. Okay. All right. Now we will start getting that same answer being written. Yes, yes. Of course, the answer is the answer is going to come up. Okay, let's look at it this way. Of course, I love to draw pictures so that at least everyone can be able to relate to this. They said we have how many women? 5 of them. And we have how many men? 4 of them. So if we have, obviously we are having, they're supposed to sit in a row, right? So say we have, that means we'll have like, let's say 9 different seats. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you're going to be able to arrange these women in such a way that no 2 women can sit next to each other, this is the arrangement you will have to follow. Woman must come first because you have only 4 men. So the 4 men will be between 2 women, if you can get that. So if a woman is here, a man must be here because the man will be the one preventing them from sitting close to each other. So if a woman is here, if a woman is here, of course you're trying to ensure that the 2 women cannot sit next to each other. So the men will be the one sitting here. So the better way to ask this now is in how many ways can this happen? So look at it. 1, 2, 3, 4, 5. We have 5 different women. If you want to ensure they cannot sit next to each other, all you have to do is to just keep permutating these different 5 rows. These 5 seats you have. That's 5 seats. So that will obviously be 5 factorial because you can arrange these seats that are meant for the women now. You can arrange it in 5 different ways. That means it's possible for you to say, this particular woman come here, this woman come here, and you keep doing that swapping. The number of ways you can do that swapping for these 5 different seats is 5 ways. Is more like you have 5 seats and you're arranging the 5 seats. You have 5 women, you're arranging the 5 women. So it's going to be 5 arranging 5 of them. That'll be 5 factorial. And that for the man will be what? of course, 4 factorial also. So that will be what? 5 factorial times 4 factorial. What does it give you? It obviously will give you 2,880. So now let's get right into Romeo and Juliet now. So you're going to see how technical this question can get. I'm going to see who is going to get the answer. So Romeo and Juliet, together with their 7 friends, will go to a birthday party. Romeo and Juliet, together with their 7 friends. Romeo and Juliet, together with their 7 friends. Romeo and Juliet, together with their 7 friends. They want to go together to a party, to a birthday party. All right. Now, they are about to sit in a row. So there is a row. Of course, you know what a row is. They are about, I mean, Romeo and Juliet with these their 7 friends are about to sit in a row. Now, how many different sitting arrangements are possible? That's the question now. How many different arrangements are possible? How many different sitting arrangements are possible? Look at the condition now. How many different sitting arrangements are possible if Romeo and Juliet, wants to sit beside each other? How many differences? Of course, you understand why Romeo and Juliet may want to sit next to each other, right? So what are the different possible arrangements, sitting arrangements? So let's see now, how do you go about this? So what's the answer? What's the answer? Look at the question and understand what's going on here. Somebody is shouting goodness here. What in goodness is wrong? Romeo and Juliet together with their 7 friends. Now there is Romeo and Juliet, and there are 7 of their friends. They went to a birthday party. They're about to sit in a row. That means obviously we have 2. Romeo and Juliet are 2 people. Then we have 7 friends. That means we have 9. We obviously have to have 9 different seats. We have 9 different seats now for both Romeo and Juliet and their 7 friends. Now, they're about to sit down in a row. Imagine all of them wanted to sit down. While they were about to sit down, Romeo was sitting here before. Someone wanted to sit here. A friend wanted to sit here. Another friend wanted to sit here. They wanted to put Juliet here. But Romeo and Juliet said, of course, it's not possible for that to happen. We have to sit down here next to each other. We want to sit down beside each other. We must be, we're not considering if you give us the first and second seat, but just make sure that we are sitting side by side with each other. So the question now is, how many different seating arrangements are possible if these two people must sit down next to each other? If you want to really understand this way. You can put Romeo and Juliet here and put their 7 friends. Of course, you can put Romeo and Juliet in this place. You can put Romeo and Juliet in this last place, and all their 7 friends are here. You can put Romeo and Juliet here, but the only thing you must never do is to put somebody in between Romeo and Juliet. How do you do that, guys? Let me explain it to you. When you have situations like this is another aspect I probably have not hammered on. Let me hammer on it at this point. When you have a question that said 2 people must be seated side by side, or 2 people must be close together, you know one thing you do when you are dealing with permutations or such situations, you will take those 2 people as one. So now, look at it. Let me just act like Romeo and Juliet were here, and this is 1, 2, 3, 4, 5, 6, 7. This is their 7 friends. What you want to do to ensure that this condition is fulfilled, because they must be together, that's what they just said, they must sit together, is that you will take Romeo and Juliet as one object. All right, you will take Romeo and Juliet as one object. So now, normally you were going to say there were 9 objects before, because you will say 7 people with 2 Romeo and Juliet being 2. You would have said 9 objects normally if this condition did not come out. All right, but because of this condition, you have to look at it as 8 objects. It has to be seen as 8 objects. So instead of you looking at it as 9 objects, you be seeing it as 8, because this Romeo and Juliet will be seen as 1, because anywhere you take Romeo to, you must take Juliet. So imagine you see this as 1. That means anywhere you pull this in out from, if you pull this and put it here, of course, the rest will have to shift Romeo and Juliet. So it will be seen as 8 objects. That's the way you solve questions like this. Rather than seeing it as 9, you see it as 8. You will pick Romeo and Juliet, the ones that must never leave each other, as 1. That's the way you do it. Now, so generally now, you would have said the way you were going to do your arrangement would have been 8 factorial, because it's 8 objects now. You want to permutate, you want to arrange 8 objects. That will be 8 arranging the 8 of them. Of course, you understand this is the same thing as 8 factorial. So you have 8 objects, you want to go on to arrange 8 objects. Now, that's 8 factorial. But you will be wrong if you wrote this as the answer. Do you know why? Because what I wrote here was Romeo and Juliet. You could still have, the condition was just that they should sit close to each other. The condition did not say Romeo was come first, Juliet coming second. It's actually possible for you to have Juliet and Romeo. This is still fulfilling a condition that they must sit beside each other. If you have Juliet first and Romeo second in the sitting arrangement, it's still okay. This still fulfills the condition. So you need to also bring this situation into consideration. So imagine I wrote, let's even say this was one of the arrangements. 1, 2, 3 of their friends, then Romeo and Juliet sat here, then 4, 5, 6, 7. You need to know that another different arrangement is still going to occur if all the friends remain where they are, and Juliet stood there and Romeo stood here. It's still, this is a different permutation. All right, so you need to consider that the possibility of always having if you have 1, 2, 3 Romeo Juliet, 4, 5, 6, 7, you could still have 1, 2, 3 Juliet Romeo. So that means for every this thing, you'll be having 2 different ways of sitting both Romeo and Juliet. So that's why you have to have your final answer as 8 factorial times 2 factorial. This 2 factorial is representing the number of ways you can arrange Romeo and Juliet. It can be either Romeo and Juliet. Of course, these are 2 objects. How many ways can you arrange 2 objects? That's 2 factorial ways, which is 2 ways. It can be Romeo Juliet or Juliet Romeo. That's what is factored in here. So the final answer you will have here will be what? 80,640. Now, this now brings me to, I gave you something under when we started this this class tonight. I gave you something that was quite very interesting when I was dealing with the physics and chemistry books. Now look at something. Look at the next question I'm going to ask you from this particular question. In how many ways can you arrange this seating arrangement if Romeo and Juliet do not want to sit beside each other? Can anybody give me the answer to that? In how many ways can you arrange this seating arrangement if they do not want to sit beside each other? Can anybody give me the answer to that? Now, you don't want them to sit side by side now. It's now, before, probably they broke up, probably they fought, probably something happened. All right? Who knows? Now, Romeo and Juliet said, you know what? I'm not going to sit near each other. We're not going to sit near each other again. Romeo, go your side. Make sure somebody is in between us. In how many ways can that happen if Romeo and Juliet must not sit beside each other? In how many ways can that happen if Romeo and Juliet must not sit beside each other? Now, I see people saying 9 factorial. Now, let me tell you why that will not be correct. I told you when we were solving that question around physics, chemistry, botany, and zoology, I told you that in that situation, everything that happened when physics, chemistry, and botany and zoology must stick together, I told you that all those things are embedded inside the general permutation. Look at this one now. If we don't have any condition attached, that means if we just said there is 9 different people, of course, Romeo and Juliet included, and 7 friends. I said there are 9 people. If I told you now that help me to permutate these 9 people in different sitting arrangements, 9 people, I didn't give you any condition. 9 people. I told you already in permutation, we look at those 9 people as objects. So we have 9 different objects. If we have 9 different objects, you have 9 different objects, you want to arrange the 9 of the whole 9. That will be 9 arranged 9, 9 permutation 9. That will be 9 factorial. All right. That's how you're going to arrange 9 of them if there were no conditions at all. But look at the condition that was attached now. The condition said that among those 9 people, Romeo and Juliet, they must not be near each other. See, inside this 9 factorial I wrote here, I want you to know that situations will arise. This answer will have situations where Romeo and Juliet were sitting near each other, because you did not if it's not, this is not free from Romeo and Juliet not sitting near each other. That means if I have, let's say these are the 9 of them. Now it's possible that, of course, 4 Romeo, 5 Juliet. This is one of the things that is going to be inside the 9 factorial. But I want you to know that in this 9 factorial, you will still have a situation where Romeo and Juliet will sit near each other. And that's the reason why the way to solve this is that you will do the general one where you don't care about either they are sitting or not sitting, which is this one, 9 factorial. You're just arranging all of them anyhow. You're not caring if you are sitting near each other or not. You will now go on now to subtract from it all the moments when they sat near each other. So the answer to that question I asked, if they must not sit near each other, will be 9 factorial minus this 80,640. Because in this case now, this 9 factorial, I told you, using that book scenario, it has all these possibilities also inside. This 80,640. We have situations where Romeo and Juliet were sitting near each other in this 9 factorial. So by subtracting this 80,640 ways, we are extracting out from that general situation moment where Romeo and Juliet were sitting near each other. So in that case, the answer left after you do this subtraction, you'll be left with situations where none of them are sitting near each other. Does it make sense to you guys? So if you do this, what does it give you? You'll be getting 282, 240, right? How many of you could flow with what I just said? How many of you were able to flow with what I just said? Like we have 9 factorial. This 9 factorial is just you arranging the 9 different objects, right? We're arranging the whole 9. We're not caring if they are sitting near each other or not. Inside this 9 factorial, there are cases where they will sit near each other there. And there are also cases where they will not sit near each other. They're in 9 factorial. But don't forget, we already knew that from our previous question that there are 80,640 ways of ensuring that Romeo and Juliet were sitting near each other. So one thing we just have to do is to go on to extract all those ways out from the general answer. And then that one will be getting an answer that is now pure, that is free from when they are sitting near each other, which is going to be this answer, 282, 240. Now, the last question for the night, you must not miss this one now. It's also on Romeo and Juliet. This is the one I expect. Now that I've said this, no, somebody's asking if there are more than 9 chairs. If they are not more than 9 chairs, it doesn't really matter. It doesn't really matter if they are sitting, if there are more than 9 chairs, because you are not arranging on the other chair. Your arrangement must only cover the objects you have. You only have 9 objects. So if there are more than 9 chairs, you would not be using the other chairs. Obviously, it's only the chairs that you have your objects for you'll be using. So look at this question on Romeo and Juliet. Let me see how you're going to fare with this. Romeo and Juliet together with their 10 friends this time. Together with their 10 friends. 10 friends now, not 7. So Romeo and Juliet together with their 10 friends. They want to go to a birthday party now. Of course, probably this time around, this is a different birthday party now. They're deciding to go with not 7 friends now. They're going with 10 of their friends. All right. So Romeo and Juliet together with their 10 friends will go to a birthday party. Now, look at the case here. They are about to sit around a circular table. So this time they're not sitting in a row. They are sitting around a circular table. They are about to sit around a circular table. Now, how many different sitting arrangements are possible if Romeo and Juliet want to sit beside each other? How many different sitting arrangements are possible if they want to sit beside each other? You people are talking about goodness again. Look at this question now. Romeo and Juliet now, they're having 10 friends, no longer 7. Maybe they made some more after the first birthday party they went for. Now they have 10 friends now. They want to go to another birthday party. And this time around, probably they're going to a different spot where the table now is not, they're no longer sitting on the road, they're sitting around a circular table. All right. How many different sitting arrangements do you think is possible if Romeo and Juliet insisted that they must sit beside each other? Okay, somebody is talking about, let me see. Okay, I saw somebody saying something around. I think somebody was setting a question. He said, okay, he said, what if Romeo and Juliet stay away from each other, but 2 people are in between them? Well, all these different other questions that could pop up, I want you to understand that all of them, of course, it's not just any question you will see on a permutation and condition. Sorry, permutation and combination, because some questions are not very practical to solve. Not impossible, but not very practical to solve. So many of all these questions that can come up where you probably will say 3 friends will be between them, it's very solvable. But in the end, you will not majorly see questions like that because it doesn't give you, there's a roadmap to hit. It's not very easy to find. You will have to do a lot of work to get some of those answers. But again, it's solvable, but not just very examinable. All right, what's the answer? Let me get my answer. I want to, somebody said 10 factorial times 2 factorial. Someone said 10 factorial times 2 factorial. Okay. Now, because of time, let me do this for you. All right. Now, this time now they are around a circular table. You already understand this is a cyclic permutation scenario. You have Romeo and Juliet, and then you have 10 friends. This means we have a total of 12 objects. All right. 12 objects. Is it not? Good. Now, if we were just told to just arrange these guys anyhow, we don't care about any condition if they have to be together or not. We will just have done this on a circular using cyclic permutation scenario where we will say this will be 12 minus 1 factorial, that will be 11 factorial. But there's a situation happening here, guys. Please pay attention. Romeo and Juliet, even though we counted them as two objects here, but because of this condition that they said they want to sit beside each other, you have to see them as one object, as I said already. So now it's like we have Romeo and Juliet as one object. Then we have the rest 10 now. So it's like normally you would have counted this as 12 objects, but because of this condition of them sitting near each other, this is just 11 objects. So we're having just 11 objects now. So if we want to permutate 11 objects, how do we permutate 11 objects around a circular table? Of course, using the formula n minus 1 factorial, this will be 11 minus 1 factorial. That will be 10 factorial. So someone sits down there and says, this is the answer, I've gotten the answer. Oh, you may be wrong because you are forgetting something. You know what you guys are forgetting? You're forgetting that even though they must sit near each other, you're forgetting that sitting near each other doesn't mean you could not also have Juliet, Romeo. So you have to put that into consideration also, that we could have Romeo, Juliet, or Juliet, Romeo. In that case now, we'll be saying 10 factorial times, considering that possibility, that can happen in two ways, times 2 factorial. So this way, this will be the answer. That'll be 10 factorial times 2 factorial, which will give you 7,256,000, or sorry, 257,600. So these are the different arrangements you can have to achieve this scenario. All right, let me give you a take-home assignment for tomorrow. This is where we're going to stop the class today. I believe you guys have learned so much and you've learned so hard. We are almost done with permutation. Okay, this is your account balance, right? That's nice. That's nice. Somebody said this is account balance, 7 million. Yeah, we are continuing tomorrow. We're continuing tomorrow. And this is what we're going to start with tomorrow. Look at the question we're going to start with. Find the number of ways we can arrange the letters of the word HELL. That's L, such that question number 1 said the two L's will always be together. Question number B said the two L's will always be apart. So look at the question you are going to be solving as your take home. There is class tomorrow, all right? Find a number of ways we can arrange the letters of the word HELL such that two L's will always be together and also two L's will always be apart. So this is the assignment against tomorrow. All right. And tomorrow we'll be continuing with a very important aspect. We have several other things to still talk about. This is a very, as I said already, examinable part of mathematics, A-level mathematics. So I don't see how you're going to avoid questions like this, right? So there are many other questions that can come out. Equations involving permutations, and then also we have not done so much around combination. So make sure you work on the assignment, and we'll meet tomorrow by God's grace. All right, guys. Thank you very much for joining. We still have probability to talk about, so let's see how fast we can go. All right. Thank you very much. Do enjoy your night rest, and we'll see you tomorrow. Bye bye.